All right. Welcome everybody to the stream. Welcome everybody to. Sorry, I had the stream audio still on. How's everybody doing? Right? Enjoying our day 5 of quarantine. Um, yes. Yeah, I like this layout too, David. My college class, I have to do some other stuff and have to have some other things going on because of just the way I have that class structured. Um, but yeah, no, I like the aesthetic of this layout a lot more. Um, hey, Valen. Naya, make sure the stream volume's up if you can't hear me. Um, the little volume in the bottom left. Um, make sure your speakers are good. Yes, Drake, you have missed the last 2 days. I noticed you just joined the Discord yesterday, so you get to go back and watch a bunch of YouTube videos and try to get caught up. Oh, right. Yeah, sorry, I'm dumb. My brain's not fully working yet. Hey, I'm allowed to be a little sluggish in the morning too. Oh, the speaker wasn't connected. Good job, Naya. I'm glad you can hear my voice as I try to teach. What's going on? We got a couple more minutes just to let people join into the stream. Yeah, it took me a second to realize it too. I was like, wait, what's the problem? Trinity's got the hookup on free audiobooks apparently. I actually haven't talked to Alex, David. I've been too busy with all of this stuff. I haven't even really gotten a chance to play League, but I'm sure Monday for practice he'll be talking all about Wukong. Nice new mouse, Valen. Oh, so 11 and 12, Cooper, we're gonna make that due. I think I decided on Tuesday. Let me double check. Yeah, probably Tuesday. That's a pretty good Alex impression, David. Yeah, we're gonna say Tuesday on that, Cooper. Yeah, I think I originally had said Monday, but I think I'm gonna post the key. Yeah, I think I'm gonna post the key Monday and then have it be like cut off for submissions on Tuesday. Just to make sure everybody gets a chance to have their questions answered and work through it and things like that. Well, what else? What else we got? What else is going on? So Lauren, an emote is just like it's I guess, let's see, emotes it's really just an emoji, but some of them are animated, some of them are custom, some of them are all kinds of things. So yeah, 100 dogs are crazy, man. Yeah, Tiara. So reminder, if you ever need homework help, I'll be in the class Discord from 12 to 2. A lot of people jumped in yesterday and got some help on some stuff. So I'll be there again today for some help on some stuff. I was going to review the assignment and do a couple questions from yesterday. I was going to do just a few quick examples. So hopefully that'll be enough. So there's a good example of an emote, Lauren, is David using his poggers in the chat. Yeah, so smiley face, yeah, whatever. Don't be stealing diamonds, Johnny. Everybody's give me them poggers in the chat. So Annika, like I said, I honestly, I think school's going to be out for a very long time. I think at the earliest, it would be after spring break. Um, Gosh, you guys are spamming bloggers. It didn't work, Cooper. But yeah, no, the earliest is going to be spring break. The reality is we're going to be doing this for the next few weeks, like no question about it. Um, so yeah. All right, that's enough OOs and UUs. Let's do a couple just kind of practice similar problems from yesterday. Um, yes, you're right, Drake. It changes. Um, Oof. Yeah, I know a couple of the AP teachers that are not as digitally inclined have decided to just spam copies and print them out to everybody. So, no, we're not going to do class over spring break, Hunter. They still want to reserve spring break as a break as it stands now. Of course, that could change. Everything changes every day. Um, so if like I said, as it stands now, the first full week of um, April, April 6th through the 10th, we will not be having school. So. No, Kate, still 8:30, but you can sleep in tomorrow. No class tomorrow, I promise. Oh my gosh, Cooper, I'm gonna ban you. Okay, so let's talk about a couple example problems from yesterday. So I wanted to just do just kind of a couple general ones. So let's look at something like we'll do say calcium chloride, CaCl2 solid. We'll look at let's look at sulfur trioxide. We'll do nitrous acid, HNO2. I don't know, I think it's a gas. And we'll do sulfuric acid. Okay. So what we're going to do real quick. Okay. All right. So stop with the emote spam. We're going to get started into chemistry. All right. So calcium chloride, sulfur trioxide, nitrous acid, and sulfuric acid. These ones aren't necessarily on. They might be on the assignment sheet. I don't remember. But I'm going to use them as just examples. So first off, what we have to do is we're going to draw what happens when these dissolve in water. Okay, so they're going to turn into aqueous. So our calcium chloride is going to turn into an aqueous. So what we need to ask ourselves is we need to ask ourselves, what kind of compound is it? Okay, is it ionic? Is it a molecule? Is it an acid? Is it a strong acid or a weak acid, right? And so as we look at this, because we know calcium is a metal, we know that, as Cooper was pointing out, it was ionic. Yeah, it is ionic. You're right, Cooper. Right? So it's ionic. So we know that ionic compounds, when they dissolve in water, they split into their ions. So calcium chloride is going to split into the calcium ion, Ca2+, aqueous. Right? We know calcium's a 2+ because it's in the second column. And we know that chloride also, right, is going to split apart too. But we got to remember there's 2 chlorines here. So this 2 should come in front to make 2 Cl-. We don't want to keep the 2 after the chlorine because that would imply some weird molecule. And it's not. It's just an individual ion. If this had been like a polyatomic ion, we would want to keep the number on the bottom. No, Xander, this is just review from yesterday. This is just more practice. If you want to jot it down in your notes, you can. Okay, so ionic compound splits apart into its ions. This 2 on the chloride comes in front, right? So the bottom numbers are going to come in front unless it's part of a polyatomic ion or a molecule. Okay, so SO3 is a gas, okay? Both sulfur and oxygen are nonmetals. because sulfur and oxygen are both nonmetals, it's going to stay together as a molecule. Okay, so since it stays together as a molecule, we know it's going to be just SO3 aqueous. Because as we remember, molecules don't split. Molecules stay together. Two nonmetals together makes a molecule. Molecule stays together, aqueous. Okay. Now, nitrous acid. We know it's an acid because it starts with hydrogen. Okay. There's two exceptions to that: water, of course, and hydrogen peroxide. There are compounds that we write that start with hydrogen that aren't acid. But almost always, if a compound begins with hydrogen, we can assume it is an acid. Oh my gosh, Shannon. Okay, so HNO2. So we have the hydrogen, right? Now, an acid splits if it's a strong acid. Olivia. So don't forget, this isn't sulfite, right? SO3 minus. This is sulfur trioxide. Okay, this is a gas. This is a molecule. It doesn't have a charge. If it were sulfite, it would be in a formula with a charge. And so molecules don't have charges. They stay the exact same. We just change it to aqueous. Okay. All right. Now, nitrous acid. Is nitrous acid strong or weak? Tyler says weak. It is, right? Because nitric acid, HNO3, is strong, but HNO2 is weak. That one oxygen makes a difference. It changes it from being strong to weak. So if remember, weak acids stay together. They do not split. And so this is going to be just HNO2 aqueous. Okay. Sulfuric acid, just to kind of get through this and move on to today's lesson. Sulfuric acid is a strong acid, and so it's going to split. Because there's two hydrogens, these two hydrogens are going to come in front. So it's going to be two hydrogens, two hydrogen ions, 2H plus, and a sulfate ion, SO4 2 minus. So notice with the sulfate, the 4 on the end pops in front. It's like 5 seconds, Tiara. You can wait 5 seconds. You guys are just so impatient. It's not that far behind. Okay. Okay. Cool. All right. So then the other question we would be asked. The 4 doesn't come in front. Yeah, and you're right, because sulfate as a polyatomic ion should stay SO4. Three seconds. See, I told you, Cooper. Tiara, what's your question? Okay, so you bring the number in front if it's not part of a polyatomic ion. Okay, you pull the numbers in front if it's splitting and it's not part of a polyatomic ion, right? So the reason why this 2 for the chlorine came in front is because Cl2 is not a polyatomic ion. There are 2 chloride ions which are Cl minus. In the H2SO4, this O4, there are 4 oxygens, but that's sulfate. Sulfate is SO4. It's a polyatomic ion. And so you don't drop it in front. Okay? So you only bring the numbers in front if they are not part of a polyatomic ion as you're splitting. Okay, hopefully that works. Now, well, the other thing I wanted to do is I wanted to ask, would these be weak, strong, or non-conductors? Right? So you bring it in front if it's not part of the polyatomic ion. You just put the charges on. Whenever you split, you include the charges of the individual ions, whatever those ions are. Yeah, it doesn't split because it's a polyatomic ion. Okay. So whenever you're looking at these things, whenever you do have to split, it's only ever going to split into 2 things. You're never going to have something split into 3, 4, 5, 6, whatever. It only splits into 2 ions, 1 positive, 1 negative. Whoops. The polyatomic ion charges you have to memorize. If it's an element, it's on the periodic table. But if it's one of the polyatomic ions, you have to memorize it, Tiara. So you have to go back and look at your flashcards. All right, so let's see if we can figure it out. Cooper, Cooper, you're a little overconfident. You got the first one wrong. So, because this is an ionic compound and it's dissolved, we're looking at how it's dissolved, okay? So if it has dissolved, I'm not looking at this side, I'm looking at this side, okay? So if it's dissolved, it's going to be a strong conductor, okay? This one is going to be a non-conductor because it's a molecule, right? Molecules don't conduct. Weak acids are going to be weak conductors, and then a strong acid is also going to be a strong conductor, okay? Yeah, strong, non-weak, strong, okay? And that's for, so this would be for calcium chloride aqueous, I ran out of room, SO3 aqueous, HNO2 aqueous, H2SO4 aqueous. Okay, so if we had calcium chloride aqueous, it would be strong. Sulfate aqueous, or sorry, sulfur trioxide aqueous would be non. Nitrous acid aqueous would be weak. It's a weak acid, and sulfuric acid aqueous would also be strong. Yeah, so I'm asking about after it's split, because technically, if I had asked about calcium chloride as a solid, it would be a non-conductor. But once we've dissolved it in water, it becomes a strong conductor. So yeah, ionic compounds, when they're dissolved, are strong, but when they're in the solid state, they are non-conductors. So you do have to watch out for the state. When I was asking about weak, strong, non here, I was asking about after they had been dissolved. Yeah, Drake, you're a little behind. The ocean is very conductive, yeah, and yeah, that's a good observation. Because it has so much salt dissolved in it, and it has so many dissolved ions, it's going to be a pretty good conductor of electricity. And weak acids are weak conductors, Tyler, yes. And it's conductive because of the dissolved salt. And we get the salt spam in the chat. Okay, that took a little longer than I wanted it to. Hopefully that gave you guys enough that you can work through Roman numerals 11 and 12 on the assignment sheet. No, you just answer them how they're written, Sadie. So if it's written as calcium chloride solid, you would identify it as a non-conductor. If it's written as calcium chloride aqueous, it would be a strong conductor. So you have to look at the phrase. So salt in the solid state, Johnny, is not conductive. But if you liquefy it or dissolve it in water, it becomes conductive. Yeah, pretty much, Lauren. You can break it down into, at least in terms of the splitting ones, when you're writing how it splits, we have ionic molecules, weak acids, strong acids. Okay, cool. Let's get into the notes for today. So today I'm going to talk about big letter C. Properties of solutions. Okay. Thanks, Tiara. All right, so letter C, properties of solutions. The first thing we're going to talk about is I want to talk about some qualitative properties first. So number one. All right, so let's talk about some qualitative properties. Remember, when we say qualitative properties, we're talking about things that aren't necessarily associated with numbers. We're talking about qualities. We're talking about things that we can tell just by looking at something. Tara, don't be rude. All right, so qualitative. So property solutions, qualitative. We're going to do 3 ways to describe something as with qualitative. Right, we're going to call it unsaturated, saturated, or supersaturated. All right, I'm gonna have to ban a couple of you. So you guys realize that Weaver does go back and watch these streams, right? All right. So, okay. So supersaturated, right? So we have unsaturated, saturated, and supersaturated. Okay. When we talk about this, okay, unsaturated means like basically what it sounds like. More solute could dissolve, right? So it means if we have a solution, they just got timed out for saying Weaver sucks. All right, so more solute could dissolve if possible. So the idea is that if you have an unsaturated solution, you could dissolve something. So if you have some sugar in some water, some salt in water, and it's unsaturated, if you were to add more salt, right, it would continue to dissolve. It would dissolve. Okay, if you had an unsaturated solution. If you get a saturated solution, then no more solute should dissolve. Right? If you try to add more salt to a saturated solution, yeah, Cooper. So more solute could dissolve, no more solute should dissolve. So if you have an unsaturated solution, you could dissolve more solute if you added more. If it's saturated and you add more solute, it's just going to sink to the bottom. It's not going to dissolve. It's at the point, the maximum capacity. Okay, so saturated means that if you add more solute, it just sinks to the bottom and doesn't dissolve, and it sits as a precipitate is the term. Now, supersaturated is a kind of an unstable condition. Obtained by manipulating temperature. Basically, more solute is dissolved Okay, I know I wrote a lot there, right? Yeah, I'll bring up some images. I'll talk about some pictures of this in a second, Lauren. I've got a video. Okay. Yeah, too much in salt in the water for saturated. So Tiara, if you're adding hot chocolate, temperature does affect saturation. Yeah, we'll get to that. So if you're adding hot chocolate, right? You're adding scoops of hot chocolate. Eventually it comes to a point that it's not going to dissolve anymore. Right, so you've got you're adding your scoops, you're adding your scoops, you're adding your scoops. Eventually, you're just going to get solid chunkies on the bottom, and they're not going to dissolve. Okay, so there's that point where it becomes saturated. So when we talk about temperature, yeah. So for most substances, Matthew, at a higher temperature, I think that's Matthew. At a higher temperature, you have more substance dissolved than you do at lower temperatures, right? So a hotter solution can dissolve more stuff than a cold solution. And so the way you obtain a supersaturated solution is you increase the temperature, dissolve a whole lot of solute, and then you slowly lower the temperature back down. And for some substances, when you slowly lower the temperature back down, the solute stays dissolved even though it shouldn't be dissolved. Okay? All right. So we've actually already done this in class. We've done a demonstration of this. So I'm going to show you a quick video of it. This was from another teacher from Cottonwood. moved up to Idaho, but I worked with him a lot at the U. Quick 1 minute 45 video of him demonstrating a supersaturated solution.
Go ahead.
All right. So we have a supersaturated solution. There's more that can normally be dissolved in there at room temperature. It's very unstable. One way to get it to come out of its supersaturated state is just by vibrating it. Sometimes when I set it on the desk, that's enough for it to come out of its supersaturated state. Or the coolest way is by adding a seed crystal. So seed crystals of sodium acetate will allow those ions that are in their supersaturated state to recognize the crystal structure of these sodium acetate crystals, and they'll be attracted to it. And as that seed crystal gets bigger, more will be attracted to it. And as that gets bigger, more will be attracted to it, and exponentially gets larger until it goes back to its saturated state. Let me show you. Just a couple crystals. And if you zoom in, you might be able to see that sort of suspended in the middle of the solution there. And then those at the front of the room in just a moment will be able to see that begin to grow. Can you all see that? So now, when that crystal finishes growing, what type of solution will I have again? So it's gone from supersaturated back to its... Well, let me pick this up and just hold it at an angle for you. And you guys can see that there's much of the solution here. This part of it's completely saturated, isn't it? And you can see the large crystal that we've made at the bottom. It looks almost like a solid chunk of ice, doesn't it? Now also, when you feel the bottom of this flask, it feels quite warm. And we'll talk about why that's so in just a sec.
All right, so let's talk about what happened, right? So the idea, we did this in class. We've shown this before. We did this as an example of an exothermic reaction because we were forming bonds. But the idea here is that we've got a supersaturated solution. We add a little tiny bit. Yeah, mine was even more saturated, Ellie, so it became totally solid. He did that on purpose so that there would be some liquid left over, and he talked about how if you take a supersaturated solution and you pull all the extra solute out, you're left with a saturated solution. Okay. All right. Cool. Next. Number 2. Let's see, could you also pull out enough solid to make it unsaturated? And yeah, the only way to do that would be to add more solvent, right? So if you added more, oh, sorry, Tara. Yeah, let you get that down real quick, since we're still want to talk about it. If you add more solvent, like if you add more water, then you could make it unsaturated, but there isn't a way to pull out enough solid to make it unsaturated. The solid's going to stay in there. I guess maybe if you lowered the temperature, filtered it out, and then raised the temperature back up, might be a way to do it, but the easiest way to make something from saturated to unsaturated is just to add more water. So you'd have to filter it, Lauren. So if you filtered out all the solid, and then took that liquid and added more liquid to it, then it would become unsaturated. So if you left that solid in there and added more liquid, then it would remain in the saturated state. So the crystal it formed was, well, the crystal it formed is a solid. It's a precipitate. The solution is no longer supersaturated. The remaining liquid is saturated. You have a saturated liquid and you have a solid. But when it was hotter, when we heated it back up and we got everything to dissolve back in, then we recreate the supersaturated condition. Okay. I'm moving on, Sarah. Would the solid start to dissolve if you add more liquid? Yes, Drake, it would. It would. More of the solid would start to dissolve. But if you filtered it and then add more water, it would be unsaturated. Okay, number 2, colligative properties. Okay, so colligative properties are properties that change when you make a solution, right? So when you compare, say, salt water to pure water, there are some properties that change. One of the properties that changes, the first property that changes that we're going to discuss, is the vapor pressure. Now, if we remember, vapor pressure is where we have our solution, whatever our solution is, right, or liquid or whatever. Vapor pressure is the tendency of it to turn into a vapor. And so it's how quickly it evaporates. In class, we did the analogy of where, or I guess we did the example of where I covered one of my hands in water and the other hand in acetone, and the acetone hand evaporated a lot more fast, or a lot more quickly, because acetone has a much higher vapor pressure. So, talk about vapor pressure. When we make a solution, the vapor pressure of a solution is lower than a pure solvent. Okay. Stop talking about Ratatouille. God, you guys are the worst. All right, so vapor pressure solution is lower than a pure solvent. When you mix a solution, the idea is that the solute particles get in the way of the solvent evaporating, right? So we drew our picture of our solute where the water molecules were surrounded by the dissolved ions, and they're kind of bonded to them that way. And so that way the vapor pressure, the amount of liquid turning into a gas state, is lower, okay? Izzy, I don't mind Ratatouille, but we're not talking about Ratatouille. All right, I'm going to start timing you guys out. Okay, let's see if we can focus now, or I'm going to keep timing you guys out. All right, so vapor pressure of solution is lower than that of a pure solvent. Because our solution is has dissolved ions in it, the solution itself can't evaporate. So if we go to letter B, because we have a lower vapor pressure, right, that means that our boiling point is also going to change. All right, so what would happen to the boiling point? If the vapor pressure is lower, we have to remember our definition of boiling point. What's the definition of boiling point? It's fine, TR. Okay, what's the definition of boiling point? So yeah, well, liquid turns to gas, yeah, but there was a more technical definition. Hey, there it is, Luke. Good chime in, Luke. So Luke says when the vapor pressure equals the atmospheric pressure, which is fantastic, okay? So if the vapor pressure of a solution is lower, that means that the boiling point has to be higher to compensate. So the boiling point of a solution is higher than a pure solvent. Okay, so salt water, for example, boils at a slightly higher temperature than pure water does. Okay. Um, did you just copy that from Google? All right, letter C. So when we make a solution, right, first thing that happens is the vapor pressure gets lower because the solute particles get in the way. And then the boiling point gets higher because that vapor pressure is lower. And so we have to have more heat and more energy in order to get it to boil. The freezing point of a solution so if the vapor pressure is higher, the boiling point would be lower. Yeah, Hunter, that's right. Yeah, if the vapor pressure was higher, the boiling point would be lower because that would symbolize, weaker attractive forces. So let's talk about a freezing point. If we have dissolved solute particles in our solvent, is it going to be easy to freeze, meaning a higher freezing point, or is it going to be harder than freeze, therefore a lower freezing point? And is guessing lower. What else? India's right. I guess if India's the only one's going to guess. It is lower, right? The freezing point of a solution is lower. Okay, and the reason why is the solute particles interfere with formation of crystals. Right? So these solute particles get in the way and they make it harder for us to freeze. And so the freezing point of a solution is lower. Now, this is really applicable in Utah, right? The reason why we put salt on the roads is that the salt actually lowers the freezing point of the ice. And so if it's, 30 degrees outside, 30 degrees Fahrenheit, normally water is going to freeze. But a saltwater solution might drop down to, 28 as its freezing point, which means it's going to melt. And so if we lower the freezing point, that causes it to be a liquid. Yeah, freezing something makes it form a crystal structure because all solids have kind of a crystal structure. Crystals is a loose term that doesn't always mean what everybody says it does. So. Yes, okay, there could be some environmental issues when it comes to salting the roads, but that's for someone else to worry about. So Meredith, if it's below 0 degrees Fahrenheit, salt on the roads will not do anything because you can only lower the freezing point so low, right? Um, oh my gosh, Phelan, you're getting timed out for that. No, you actually, so depending on how much salt you add, you actually can get the freezing point to drop almost to 0 Fahrenheit. But you'd have to add a lot of salt in order to get it to get down that low. Okay, last thing we want to talk about, letter D, is something called osmotic pressure. Osmotic pressure, we're just going to say osmotic pressure increases. I'll talk a little bit more about osmotic pressure on liquid. Yeah, Ellie, you can melt salt. Salt can be a liquid. Tyler, to answer your question, there are different chemicals that are in like the road salt. Not like it's not all sodium chloride table salt. Some of it's magnesium chloride. Some of it's some other things that actually have a greater impact on how things freeze. Okay, so yes, salt can be a liquid. Salt melts at like 800 or 900 Celsius. Okay, cool. So osmotic pressure is the last thing we want to talk about. Osmotic pressure increases. It's our last colligative property. So, recap: vapor pressure lowers, boiling point increases, freezing point lowers, and the osmotic pressure increases. I'll talk about osmotic pressure on the next page because I need to draw some pictures. Yeah, but if you melted salt, it would be like 1,000 degrees. Of course, it's gonna melt your ice. Salt freezes at 1,000 degrees too, because it's a solid at room temperature. The salt, I guess, is technically a liquid, but it's a dissolved ion at that point. Stephen, why did you shout out to yourself? Okay. It's because I answered your question, Tiara. Yeah, I guess. But as soon as it snowed or rained, it would all dissolve, Lauren. And so it would only protect you for like one storm. Yeah. Okay. Cool. These are the 4 colligative properties. Make sure you know the 4 colligative properties. So osmotic pressure, I'm going to draw a picture of that on the next page, Johnny. So colligative, real quick, colligative just means these are properties that change when you make a solution. Ellie, it would be too hot to drink, just like your coffee most of the time. It would be solid if it got cold enough for you to drink it, Johnny. So colligative properties, again, are properties that change whenever you make a solution. Okay, so let's talk about osmotic pressure in a little more detail. So osmotic pressure is when you have a semi-permeable membrane. Okay. Right. Yeah, but it's a biology thing. Yeah, so you probably have heard about it in biology. So if we take a semi-permeable membrane, okay, kind of like this cell membrane, right? The cell membrane's a semi-permeable membrane. The idea is that if you have, if we have water on this side, and if we have like salt water on this side, there's a gradient because of pressure. Okay. Oh my gosh. So semi-permeable membrane, right? Water and salt. If we have a saltwater solution on this side and water on that side, there's a pressure gradient where the salt water, because it is a concentrated solution, the water is going to flow into the salt water by a process called osmosis, where things go from if you have a high concentrated solution, it's going to flow into that. And so after time, right, what's eventually going to happen is that it will travel across the semi-permeable membrane and will get diluted. Yeah, so basically the water just goes to the more saturated, or the more side. So the idea is that the more concentrated we make this solution, the greater the pressure across the semi-permeable membrane. Yeah, the water just goes to the more saturated side, Lauren. So the reason why this is a colligative property is that it has to do with making a solution. So to go back to Cooper's question, are there any important exceptions to the rule, like freezing point increase solution? There are a couple, but we won't talk about them in this class. They'll be more for AP if you take AP. Yeah. Okay, I think I answered all the questions on that I wanted to talk about. I think this is good for the notes. So a reminder, you've got a few things. You have the assignment sheet. Uh, 11 and 12. And then you can also do you can also start the chapter 15 canvas, which I went ahead and changed all the written problems to where you actually have to write in it. Yeah, there's saltwater pools all the time. But you would have to have some sort of a semi-permeable membrane, Kate. It's the idea that this is the cell wall is kind of the big thing here. Or sorry, the cell membrane is the big thing here, this semi-permeable membrane. So the canvas is going to be due on Tuesday. There's a few last things I want to talk about for the canvas, but you can do most of it over the weekend if you want. So that's a good question, David. So when we say semi-permeable, in this case, it allows water to cross, but not salt. Right? So semi-permeable. It allows some things to go through, but it doesn't allow for other things to go through. So yeah, it basically, in this case, for this semi-permeable membrane, any dissolved ions are going to be too large to go across. So only water can go across. You should be able to finish the canvas by Monday night, Xander. But we'll do a couple more things on Monday for some more notes. Does water that can cross include water that the salt dissolved in? No, the salt has to stay behind. So if you put some kind of like reversed pressure on here, you could cause the water to go back the other direction. I moved it, Cooper. So it's pushed back a couple days. Yeah, the quarantine's been a little rough. I'm working on that, Lauren. I'll let you guys know on Monday. So for now, just make sure you have it done on your paper, and then I'll give you an update on how we're going to get it turned in and graded on Monday. Yeah, I'm with you on that, Cooper. I miss the person interaction. I think my kids are downstairs. Maybe I'll text my wife, tell them to bring them up. So much rage. All right, so this is it for the notes. This is as far we're going to go. There are a couple more things we need to talk about on Monday. I like the Fortnite llamas. Oh, Weaver's chiming in. Weaver's in the chat. Shout out to Weaver in the chat. Weaver says that he'll be available for questions from 1:20 to 2:25. So he'll be in the Discord. I've been talking to Weaver about how to use Discord and all those other things. I'm using Discord. I'll be there from 12 to 2, so feel free to join in. And I'm not going to ban Weaver. So Weaver will be on Discord. I'll be on Discord from 12 to 2. So if you have questions on either the assignment sheet or the Canvas, hop in and you'll get some help from both of us. We're at the end of the stream, so it's not a big deal. Ella, that's a good question. There are a couple calculations from the book. So there's a couple calculations for saturation that's one thing I'm going to talk about on Monday. So I decided to wait till Monday to talk about those. Tiara, you just have to unmute yourself, right? So the idea, if you're in the Discord, okay, so if you're in the Discord, you click one of the channels over here, right? So you click group 1. And then you have to make sure that your mic, you click this button
Daddy.
to unmute yourself. Hi, Gavin. Do you want to say hi?
Yes.
Here, come here.
Okay.
Here, look in the camera.
Yes.
So in right here, bud. See the camera? You say hi.
Hi.
Hi, Claire.
Oh, see color.
Give me my pen back. Okay. Good luck, guys. Have a good rest of have a good weekend. No class tomorrow. I'll see you guys again on Monday. I'll be in the Discord.
Yeah.
Okay. Bye, guys.
Yeah.